Today we will talk about multicollinearity. Sometimes two variables measure a similar concept. They are correlated, but they're not exactly identical. But the fact that they're correlated makes it hard for the regression to disentangle their individual effect on the response. And what happens as a consequence, this difficulty to figure out, is it due to that variable or this one, results in confidence intervals in the regression being very, very wide, only of the correlated variables. So it reflects the uncertainty of we don't really know is the contribution, the beta, due to one variable or the other. More generally, it needn't be two variables, it could be several variables. One variable may be correlated with a linear combination of multiple variables. And one way to measure the degree of collinearity is this concept of variation inflation factors, VIF. Let's talk first about exact collinearity. And there's a formal definition. When you have a linear combination of the x variables that is always zero, where you can choose the t's here as you want, then you have exact collinearity. The t's, of course, cannot trivially be all zero. We have already seen an example of this when we talked about indicator variables. So the idea with indicator variables, you have to take out one of the indicators to avoid exact collinearity. And in the example of male and female, we can make this fit this definition. We're looking at the intercept male and female, and we're choosing for female the coefficient 1, for male the coefficient 1. Remember, the intercept is 1. And we choose the coefficient -1, right? So T0 is -1. With this choice, we have -1 plus male, indicator of male and female. These together are always 1, and so you have -1 plus 1 equals 0. So that was exact collinearity. We talk about multicollinearity when the linear combination is not exactly 0, but approximately 0. And equivalently, we can say that we have multicollinearity when one x variable can be predicted approximately by a linear combination of the x variables. Aha, linear combination, we are back at regression. So now we can write this as a regression, replacing the approximate sign with an equal sign, but then adding error. And as always, error is distributed normally in the usual way. So the variance inflation factor is formally defined as 1 divided by 1 minus r squared. This is rj squared. Where this rj squared is the coefficient of determination, the r squared, when regressing the j's x variable xj on all other variables, x variables. It is not the r squared, the usual r squared from linear regression where you have y on x. There's no y here anywhere. Yeah, and here's the same thing, the linear regression again, where we're leaving out the j's variable because that's over here. Question for you. What is the variance inflation factor when xj is uncorrelated with the other x variables? Here's the formula, here's some answers, and I will leave you to answer this and move on to the next question. Next question is very similar. What is the variance inflation factor when xj is very highly correlated with the other x variables? Same answers, same formula. And so I will leave you with that also. And going to a fun fact. We've defined the variance inflation factor through the R squared of the J's variable. And it can be shown that the variance inflation factor of the J's variable is the J's diagonal entry of this matrix, the matrix being inverse X transpose X. And if you remember, the variance of beta, the estimate of beta, was sigma squared times that same matrix. So what does it tell us? Well, the J's diagonal element of this matrix is the variance of beta J, right? Well, times sigma squared. So we have a direct correspondence here that, well, the width of the confidence interval is directly related to that R squared, the RJ squared that we saw earlier. That connection is not obvious, but it's really cool, I think. So I'll leave you with that.